All right, in part two here, we are going to take a look at the last 5 scenarios. Well, we're really just going to group those into two. We're going to look at infinite solutions and no solutions, how those different things occur algebraically. Right? So let's take a look at this first system here. Right? Again, we don't know that this has no solutions or infinite solutions or even one solution. So we want to start the exact same way we did in the last lesson. Right? I want to label my equations. My goal is to create a system of 2 equations in 2 variables. Okay? So if I look, my y's are already set up to eliminate if I add equations 1 and 2 together. So I'm just going to go ahead and do that. Equation 1 plus equation 2. So I'm going to rewrite them. I'll have x minus y plus 2z equals 5, and 2x plus y plus z equals 7. So I will end up with 3x, the y's cancel, plus 3z equals 12. And then I need to eliminate the y's again by adding 2 other equations. So if I look at equations 2 and 3, if I multiply equation 2 by 2 and then add that to equation 3, the y's would cancel. So I'm going to write out 2 times equation 2 plus equation 3. And I'm going to go ahead and multiply equation 2 by 2 as I write it down. So that'll be 4x plus 2y plus 2z equals 14. And then equation 3 stays the same. So 3x minus 2y plus 5z equals 20. All right. So adding these, we get 7x, y's cancel, plus 7z equals 34. So now I've got my system of 2 equations in 2 variables. I'm going to rewrite those here. So 3x plus 3z equals 12, and 7x plus 7z equals 34. So let's eliminate the x's. Right? To do that, I'm going to have to multiply both equations by something here. And we said, well, the easiest way is just to take a coefficient and multiply the opposite equation by that. So I'm going to multiply the top equation by 7 and the bottom equation by 3. And we do have to make sure we have opposite signs. So I'm going to multiply or make one of them negative. Right? So that's going to end up as negative 21x minus 21z equals negative 84. And then down here, we will have positive 21x plus 21z equals 102. So when I add, the x's cancel, but so do the z's. So on the left-hand side of the equation, I just end up with 0. And then over here equals 18. Obviously, this is not a true statement. 0 does not equal 18. Whenever we get an untrue statement here, that means no solutions. Okay? Just like it did when we were solving systems of 2 variables or 2 equations in 2 variables. Okay? If we get an untrue statement, that means no solutions. All right? So visually, okay, I just want to show you what this system looks like visually. Right? So this would be what we have. Okay? We can see that these 2 planes, or I'm sorry, these 3 planes don't share any points in common. If the green and the blue planes were extended out, we could kind of create a little triangle here, and we would see that no points are shared among those 3 planes. Okay, now you will not have to do anything like this, the visual portion on a test. Okay, I'm just looking for the algebraic portion. Right, so something like this, solving down to here and seeing that these 3 planes do not share any points. Right, so I want you guys to pause the video and try the second example here. I'm not going to put a question up on the screen, right? Because we know that this example is going to have no solutions. I'm going to tell you the answer is no solutions, but I want you to pause the video and try it on your own before you see my work for it. All right, so let's take a look here. I labeled my equations 1, 2, and 3, and then I chose to eliminate the x's. Okay, so I just multiplied the first equation by -1 and left the second equation alone. When I added those together, I got y minus 6z equals 2. Then I eliminated the x's again by taking -7 times the first equation and adding that to the third equation. When I did that, I got 3y minus 18z equals 18. So then, to solve this system of equations, I multiplied the first equation by -3. And in doing that, when I added these two equations together, I got 0 equals 12, which is not a true statement. That means there are no solutions. Now, you could have done this first part a little differently, right? You could have eliminated the y's, right, instead, right? So this step might look a little bit different, but that's okay. There's more than one correct way to do this problem, okay? But at the end, we should get an untrue statement and get no solutions, okay? So visually, let's take a look at this one as well here, okay? This system of 3 equations and 3 variables looks like this. Okay, I've got 3 planes that don't share any points. We can kind of see through here that there is that little triangle that's created showing that there are no points that are shared among those 3 planes. Okay, so let's take a look then at a couple of, well, first, fill in this blank here. Okay, if we ever get an untrue statement, 0 equals k, all right, where k is some constant, that means the system is inconsistent and there are no solutions, right? That's the vocab idea, inconsistent. So let's take a look at a couple of examples then where we end up with infinite solutions. Right? So this first one, again, the goal is to create a system of 2 equations and 2 variables. So I'm going to label 1, 2, and 3. And right off the bat, I see if I just add equations 1 and 3 together, I'll eliminate the y's. So let's do that first. So 1 plus 3, and I will have x minus y plus z equals 7, and 4x plus y minus 11z equals 18. So if I add, I get 5x, the y's cancel, minus 10z equals 25. So let's try to eliminate the y's from another pair of equations. Let's see if we do 2 times the first equation plus the second equation, the y's would cancel. So I'm going to do 2 times equation 1 plus equation 2. And I'm going to go ahead and multiply 2 times the first equation as I write it down. So 2x minus 2y plus 2z equals 14. And then my second equation, 3x plus 2y minus 12z equals 11. And if I add, I will end up with 5x minus 10z equals 25. I got the exact same thing here. So this is my new system. Hopefully we can kind of see what's going to happen here. But I'm going to go ahead and write it all out. So 5x minus 10z equals 25, and 5x minus 10z equals 25. So to eliminate one of the variables, I would want to multiply one of these equations by -1. So I'm going to get -5x plus 10z equals negative 25, and my second equation will stay the same. So 5x minus 10z equals 25. And when I add these together, everything on the left side cancels, and everything on the right side cancels. We get 0 equals 0. We get a true statement. Whenever we get a true statement, that means there are infinite solutions. But we are going to take this one step further and list out the solution set, okay, all the possible solutions. So what that means, I'm going to take this equation and solve it for x. Okay, I'm going to end up writing my entire solution set in terms of z. So I want to take one of these equations here and solve it for x. So I'm going to rewrite that equation up here. 5x minus 10z equals 25. Add the 10z over. We get 5x equals 10z plus 25. Divide everything by 5, and we'll get x equals 2z plus 5. Now, what I'm going to do is take this and plug it into one of my original equations. Right? So I'm going to do it in the first one because that one looks the easiest. So I'm replacing the x with 2z plus 5 and minus y plus z equals 7. So now I want to solve this equation for y. Well, let's see, I can combine my z's over here. So I'll have 3z plus 5 minus y equals 7. Then I can subtract my 5 over. 3z minus y equals 2. Subtract the 3z over. Negative y equals negative 3z plus 2, and divide everything by negative 1. We'll end up with y equals positive 3z minus 2. So I'm going to express my final answer like this, okay? My x, I solved for x and got 2z plus 5. My y, I got 3z minus 2. And then I'm just going to write the z coordinate as z. Now, technically, we could have done this with any variable. Okay, we could have written our solution set in terms of x. I could have done x and then some equation of x and some equation of x, or I could have done it in terms of y. Just to be consistent, we are always going to write our solution set in terms of z when we have infinite solutions. Okay, so whenever we get 0 equals 0, you want to solve one of these equations for z and then plug that back in, or I'm sorry, solve it in terms of z. So we solved this equation for x and had z's on the right side, and then plugged that back into one of my original equations and solved for the other variable, in this case y. Okay, so whenever we get infinite solutions, write your final answer in terms of z. All right, there's one last example on here. Again, I'm not going to have a question pop up on the screen, but I want you guys to pause the video and try this on your own before you look at my work here. All right, so this one we get kind of an ugly answer, right? I chose to try to eliminate the x's. So I did 4 times the first equation plus the second equation, and I got 3y minus 4z equals negative 9. Then, to eliminate the x's again, I took the second equation plus 2 times the third equation and got 9y minus 12z equals negative 27. So when I solved that, right, I end up with 0 equals 0. So this system does have infinite solutions. So now what I did, I took this equation and solved it for y. So I added the 4z over, divided everything by 3, and I got y equals 4/3 z minus 3. Then I took that 4/3 z minus 3 and plugged that back into my first equation in place of y and solved for x. Okay, so my first step, I combined my like terms. 4/3 z plus z, that would be 4/3 plus 3/3, so that would be 7/3 z. Added the 3 over, subtracted the 7/3 z, and got x equals 7/3 z plus 8. So my solution set in terms of z is this: negative 7/3 z plus 8, 4/3 z minus 3, z. Okay, now visually, what that means, or what that looks like, okay, we have these all three planes intersecting at an entire line. Okay, we can see here that they all intersect in a full line. So this solution set that we just wrote down is how we are expressing every point along that line. Okay, this solution set is how we are expressing every point on that line. Same idea for the last example that we just did. Okay, this solution set is every point on the line. So here is what that third example looks like. Okay, all three of these planes intersect at this line right here. So our solution set expresses every point on that line. Right? So the final blank on your notes is just if we ever get 0 equals 0, which is a true statement, the system is dependent, there are infinite solutions, and we're going to express them like this. Okay, we're going to solve for x in terms of z, we're going to solve for y in terms of z, and then we're going to have the z coordinate just there. Okay, so the final question is going to pop up on your screen. Just what questions do you have? And we will work on some practice problems in class tomorrow.